Here I'm going to discuss what happens when you differentiate an integral. Let's suppose we have a function little f of x, whose indefinite integral can be written as capital F of x, possibly plus a constant c. You've probably seen this before, and you might also have been told to apply a differentiation process to the whole equation. That would give us something like df by dx for capital F. The c, of course, disappears because it's a constant, and that leaves us d by dx, integral f of x dx. And you've probably been told that differentiation is the reverse process for integration, and so we get little f of x. But is it really true? Can we show this more rigorously? Well, yes, but the first thing I want to do is to correct what is really rather an abuse of notation. Writing capital F of x on the right and having x on the left as a dummy integration variable is not really very good practice. The way we should write this is as follows. If we want the right-hand side to be a function of x, that is, capital F of x, we should not use x for the integration variable on the left. Instead, I've decided to call the integration variable there u. It's a dummy variable. It should never appear in the right-hand side, because after doing the integration and substituting the limits, u has been entirely substituted for. Of course, if we manage to do the integral of little f of u, we will get a function capital F, and if we want it to be a function of x, then we should have x as our top limit on the integral. For the bottom limit on the integral, we could put anything, as long as it's a constant. I've called it a. Here it would be the case that capital F of a is actually the same as negative c. In practice, since we're not very interested in the c, we normally just make a choice for a and call it 0. So in fact, I will work with the following. Integral from 0 to x, f of u du equals f of x plus c, where c happens to be minus capital F of 0. Now, let's do what we did before and differentiate. Let's differentiate the right-hand side first. We'll get d capital F by dx, and on the left we now have d by dx, integral 0 to x, f of u du. Now, instead of just telling you that we get little f of x, I'm actually going to apply first principles differentiation here. Remember how we do that? We take the limit as h goes to 0, and then we want the function, but the function is actually the integral, and it's evaluated x plus h, f of u du, minus the function at x, f of u du, all divided by h. Now, what can we do about those two integrals in the top? Well, the integral from 0 up to x plus h, remember this is really just the area under the curve. Okay, so suppose we've got some function that looks like this, and we start at 0, and here's x, and a little bit further on, here is x plus h. So the first integral as far as x plus h is the red shaded area, call that 1, and the second integral actually is the blue shaded area that stops at x. Clearly the difference is just the area, which I'll now shade in green, here. That's the integral from x to x plus h. So we can rewrite our limit by taking the difference of the two integrals is just the integral from x to x plus h, f of u du, and that's still all to be divided by h. Now that green integral, let's draw it here again for clarity. this region here, x and x plus h. The width of the rectangle is h, and the height, well, so long as h is small, the height, that's this height here, is approximately f of x. So the area of the rectangle is approximately the width h times the height. And the smaller h gets, the closer will be the approximation. And after all, we are taking the limit as h goes to 0. So this should be a good approximation to use. So we now end up with df by dx, remember, was on the left-hand side. And now we have limit h goes to 0, 1 over h. I made that look like an n before, didn't I? So let's just make it into an h, that's better. And now the integral is to be replaced with h, f of x. And now we see that the h's cancel, and if we take the limit, we just end up with f of x. So sure enough, we have our result that the d by dx, the integral from 0 to x, f of u du, is equal to f of x. So there's a more rigorous proof using differentiation from first principles of the differential of an integral, giving out the integrand that's inside.